A load balancer is a software or a hardware device that sits in front of your servers and distributes network traffic across them. I would say the main goal of the load balancer is to prevent any given server to become overloaded. The logic that the load balancer uses to distribute traffic is called a load balancer algorithm. You can think of it as a set of predefined rules. There are two primary approaches to load balancing. The first is static load balancing algorithms. They work the same way regardless of the state of any particular server, such as CPU or memory load, or how many connections are already established with that particular server. They are simpler and more efficient to implement, meaning it takes less time and resources for the load balancer itself to decide to which server to send a request. Some examples are round-robin, weighted round-robin, source IP hash, URL hash, and randomized algorithms. On the other hand, we have dynamic load balancing algorithms. They take into account the state of the backend server and consider server load when distributing requests. These algorithms require communication between the load balancers and servers, so they are slightly more complex but can distribute requests more efficiently. Some examples include the list connection method, weighted list connection method, list response time, and resource-based method. As you may have noticed, many algorithms can also use weight or preference to help decide where to send a request. Usually, you use non-weighted algorithms when all your servers have identical specs. On the other hand, if one server has more resources, such as CPU or memory, you can use a weight parameter to send more traffic to that specific server. Also, we'll talk about what algorithms are used in cloud environments, such as AWS, Azure, and GCP. Additionally, we'll cover some extra load balancer features, such as session persistence, sometimes called sticky sessions, and rate limiting. In addition, I'll provide real-world examples, mostly based on Nginx. I've packaged them with Docker and Docker Compose files, so if you want, you can quickly reproduce them on your own locally, without using any third-party services. So if your load balancer supports multiple algorithms, after this video you will have a solid understanding of which one is the best fit for your use case. Let's start with static load balancing algorithms. They follow fixed rules and are independent of the current server state. For example, they don't collect any metrics such as the number of connections, CPU, or memory utilization. However, most load balancers using static algorithms still provide health checks for the backend servers. So if a server goes down, many load balancers will remove the server from the load distribution. The first and most widely used is the round-robin algorithm. It's easy to implement and easy to understand. Here is how it works. Let's say you have 3 servers behind the load balancer. Once the first request arrives, the load balancer will forward that request to the first server. When the second request arrives, presumably from a different client, the request will then be forwarded to the second server, and the third request will be forwarded to the third server. Since the third server is the last in this cluster, the next request will be forwarded back to the first server, and the fifth request to the second server, and so on. So it's not random distribution. It starts from the first server, goes down the list to the last one, and then repeats. This way, each server gets equal opportunity to serve requests. This method is very simple, but it won't perform very well in certain scenarios. For example, if server 1 has twice the CPU and memory compared to the others, then the first server should be able to handle twice as many requests as the others. Unfortunately, a load balancer running on round-robin algorithm won't be able to treat 3 servers accordingly. Even if they have disproportionate capacities, the load balancer will still distribute requests equally. As a result, server 2 or 3 can get overloaded faster and probably even go down, and you wouldn't want that to happen. The round-robin algorithm is the best for clusters consisting of servers with identical specs. For other situations, you might want to look at other algorithms, like the one we'll discuss next. But first, let me run a quick demo. It's going to be based on Nginx. To run it, we'll use docker compose file. Here we have a load balancer service based on Nginx and 3 servers with our application. The application will respond with a server name. For example, server A will return server A response, and so on. Next, let's configure Nginx to use round-robin algorithm. It's the default, and we don't need to use any additional settings. Just specify all your servers with port numbers, and then use proxy pass directive to forward requests to the servers. You can run it locally by simply using docker compose app command from the first example. Then you can use curl to hit Nginx. For the first few times, you will most likely get a response from server A. After that, Nginx will start serving requests in round-robin fashion. Once in a while, you may get unexpected results. It's just because Nginx spins up many workers that serve requests independently. Now, for the second scenario, as I mentioned before, when the first server has higher specs than the other two, you might prefer an algorithm that takes this into account and assigns more requests to the first server. One such algorithm you could use is weighted round-robin. The weighted round-robin is similar to round-robin in the way requests are distributed between servers, but with one exception. The server with higher CPU and memory will get more requests. Now, since it's still a static algorithm and the load balancer cannot reach out to the servers to ask about resources, we would need to manually assign a weight to each server. The server with a higher weight will get more requests. It's as simple as that. If we follow our previous example and we have 3 servers, with the first one having twice the CPU and memory compared to the others, we could assume that server number 1 can handle twice as many requests as the others. We can use weight and set the weight property to 2 for the first server and 1 for the others. In that way, if we receive 4 requests, 2 will be forwarded to the first server and 1 request each to the second and third servers. Now, capacity isn't the only reason for choosing weighted round-robin algorithm. Sometimes you'll want to use it if, let's say, you want one server to get a substantially lower number of connections than an equally capable server. This could be because the first server is running business-critical applications and you don't want it to be easily overloaded. Alright, let's run a demo. Now, it's very similar to the previous example. We only need to set weight property for each server. Let's say we want to send twice as much traffic to server 1 and the rest to servers 2 and 3. By the way, the weight in Nginx defaults to 1 anyway. I just put it here to explicitly show the difference. If you run docker compose app again from the second example folder and run curl a few times, you'll notice after a few requests that server A gets 2 requests, and then requests are forwarded to server 2 and 3. That's all the difference. It's manual, and that's the biggest drawback of this approach. You can also use round-robin algorithm to distribute traffic by using DNS. In that case, you don't need a load balancer in front of your server at all. Instead, you would create multiple A records for the same domain. Each time the client wants to make a request to our server, it first needs to resolve the domain name and get IP address. By creating multiple A records, each time the client will get a new IP address from that list. There are so many problems with this approach. First of all, because of both DNS caching and client-side caching, this approach doesn't always provide evenly distributed load balancing. Another drawback is that if one of your servers goes down, the DNS server will still keep that IP address in the round-robin rotation. On the other hand, most load balancers have health checks that can immediately remove the server from the list if at least one or two requests fail. Now, to try it out, you can create multiple A records. For example, for Google domains, you can add multiple IP addresses for the same host. When you try to resolve it, each time Google domain name server will return a new IP address from the list. But of course, you need to be aware of DNS caching. Next are the hashing methods, and the most common among them is IP hashing. It combines the source and destination IP addresses and uses a mathematical function to convert them into the hash. Based on the hash, the connection is assigned to a specific server. For example, the division reminder method is the simplest one used for hashing. So in this example, we have 3 servers, which means the size of the hash table is 3. Just to make it simpler, I use decimals instead of converting IP addresses and the size of the hash table to binary. So let's pretend the source IP address is 1234. Now, if you use modular division, we get 1, which means this request will be forwarded to the second server. Now, if you have IP address of 1235, the hash key will be 2, and the request will be forwarded to the third server. So, as you can see, the hash key will never exceed the size of the hash table. The biggest benefit of this approach is that if session is broken between the client and the server, because the hash function always returns the same result, the same client will be forwarded to the same server. Another type of hashing is URL hashing. The algorithm generates hash values based on the URL present in the client request. The request is then forwarded to servers based on the hash value. The URL hash algorithm is useful when load-balanced servers serve mostly unique content per server. So all requests related to, for example, to payments will go to one server, and requests for user authentication will go to another server. Hashing is also used by cloud providers, such as AWS and Azure. For example, Azure uses 5-tuple hash, combining source IP address, source port, destination IP address, destination port, and IP protocol. A similar approach is used by AWS and GCP. If you want to try using IP hash method with Nginx, you just need to add a single setting IP hash to your upstream servers. If you run this again and try to access Nginx, all the requests will be forwarded to the same server, because your IP address is not changing. Therefore, all requests are routed to the same instance. Next is random allocation. As its name implies, the algorithm matches clients and servers randomly, for example, by using a random number generator. Unlike algorithms like round robin, random allocation doesn't follow a predefined pattern or consider any server metrics. It simply picks a server at random each time a request comes in. On the other hand, similar to round robin, this algorithm is best for clusters consisting of nodes with similar specs, such as CPU and memory. Nginx supports the random algorithm with 2 choices. We'll use just the random option. When you start the compose file and send requests to Nginx, it will each time randomly select a server and forward your requests to it. The next group is dynamic load balancing algorithms. Unlike static algorithms, they examine the current state of the servers before distributing traffic. They can collect data on CPU and memory utilization, along with other metrics. Dynamic algorithms are also frequently used with health checks, so if a backend server fails the health check, it gets removed from the pool. A connection is open communication channel between a client and a server. When the client sends the first request to the server, they authenticate and establish active connection with each other. In the least connection method, the load balancer checks which servers have the fewest active connections and sends traffic to those servers. This method assumes that all connections require equal processing power for all servers. This algorithm is most appropriate when you have requests with different connection times, especially when you have a lot of persistent connections, such as WebSockets. Now, because additional calculations are required to determine the server with the least number of connections, it may increase the load on the load balancer itself, and it can become a bottleneck. Nginx also supports this type. You can use least con option in the upstream server. For this demo, I'll keep only 2 servers, just to make it simpler. I also have another endpoint in my application to simulate a long persistent connection. Alright, this time let's run compose in the foreground. When we request the poll endpoint, it'll simulate a new persistent connection, and from the logs you can see which server was used to establish it. Now let's start hitting the about endpoint. It'll take a few seconds for the Nginx to collect metrics such as active connections, and after that it will start to send requests to the other server without any connections. The weighted least connection method builds on the least connection load balancing algorithm by taking into account the different specs of the servers. The administrator assigns a weight to each application server based on the relative processing power and available resources of each server in the pool. The drawback, of course, is that it's a manual step. You need to analyze and set those weights yourself. You can set weights similar to round-robin algorithm that we used in one of the previous demos. You just assign weights to each server based on CPU and memory. For example, in this case, if you have the same number of connections, out of 6 requests sent to the load balancer, the first server will get 5 requests and the second will get just 1. Next is the least response time load balancing algorithm. It is a more advanced version of the least connection method. The response time is the total time that the server takes to process the incoming requests and send a response. The least response time method combines the server response time and the active connections to determine the best server. You should be using this approach when latency is very important to facilitate the best user experience. Unfortunately, this method is only available in the paid Nginx Plus version. You have 3 options to select what to measure: time to receive the first byte from the server, time to receive the full response from the server, or also taking into account incomplete requests. The last dynamic algorithm that we'll talk about is resource-based load balancing. In the resource-based method, load balancers distribute traffic by analyzing the current server load, such as CPU, memory usage, network, disk I/O, etc. To do this, you would also need to install special agents on each server. Then the load balancer checks the server with the least load and sends a request to it. In this case, load balancers perform a detailed health check of each individual node. This method is appropriate when different requests require different amounts of resources to process a request and send a response. For example, you may have an endpoint to generate a report, which would take a lot of CPU, and another endpoint to return some static content. Obviously, if you use round robin in that case, you can quickly overload some servers. The drawback, of course, is that you need to basically maintain a separate monitoring system for your load balancer and take into account all that information in order to make a decision, which could be a CPU or memory-intensive task on the load balancer itself. The last type of load balancing we'll discuss is geolocation based. If you have clients or simply visitors around the world, you would want to provide the same level of user experience to everyone. For example, if you have a server in Los Angeles and visitors from UK, the requests or network packets must be routed all over the world. Each network hop would add latency because a router needs to receive packets, buffer some, and send them forward to your original destination. Geolocation-based load balancing assumes that you have servers around the world and a centralized load balancer which can make a decision based on the incoming client's IP address. In that way, your load balancer will forward requests to the server closest to your client, which reduces latency. Yes, routing based on IP address may not be the most accurate, and this type of load balancing may not be the best choice to evenly distribute traffic across your servers, so you would need to maintain a different number of servers in different countries. Another feature that some load balancers have is rate limiting. It's not strictly a load balancing algorithm, but it helps to protect the quality of service. It is a technique used to control the amount of incoming requests to the server within a given time. For example, you can limit the number of requests to 100 requests per second. It is often used to protect resources, prevent abuse, and ensure fair use. You can also limit the number of requests from a particular IP address. Open source Nginx also supports rate limiting. This limit is configured per client IP address. First, we use built-in Nginx variable to get IP address from the client. Then we configure how many IP addresses we should store in memory. 10 megabytes is equal to 160,000 IP addresses. And finally, how many requests from each IP address we would allow. For the demo, I'll use a very small number, like 2 requests per second. Then we add this directive to the location that we want to protect. After you start the compose file, if you slowly send requests to Nginx, you'll get a response from the server. But if you increase the rate, you'll get 503 service temporary unavailable error. The last thing that we'll cover in this video is session persistence, or sometimes called sticky sessions. The session itself is the time that it takes a user to complete a transaction or task, which might include multiple requests. Session persistence simply means that during the session, all the requests will be routed to the same backend server. One reason could be if a user authenticated on server 1, and if that user is then redirected to another server, they will need to re-authenticate. There are also some other use cases. Some load balancers, including open source Nginx, would suggest using a hash or IP hash algorithm to forward the request to the same server. Other more advanced load balancers have support for cookies and other approaches, including Nginx+. For example, if you have Nginx Plus, you have 3 options to enable sticky sessions: sticky cookie, sticky route, and sticky learn method. If you, like me, don't want to pay for the Nginx Plus, you may have to use IP hash method, but it's not 100% reliable for sticky sessions. Do you want to know the difference between forward and reverse proxies? I also have tutorials covering Kubernetes, databases, Kafka, and many other components that we most frequently use in production. I have some benchmarks as well if you're interested on my channel. Thank you for watching, and I'll see you in the next video.